Hello, my name is Jonah Wu, and this is my Physics 2211 Lab 3 black hole. The purpose of this lab in part 1 was to find the mass of a black hole by analyzing the motion of a star of known mass in orbit around the black hole. For part 2 of the lab, we were finding the initial velocity needed for a spaceship in the black hole star system to fly close to the black hole before escaping the system without crashing on the planet or the black hole. The first fundamental principle involved in this lab was Newton's second law, or the momentum principle, which states that the net force on an object is equivalent to the change in momentum over the change in time. From this equation, we can derive the velocity update formula as well as the position update formula. The second fundamental principle involved in this lab was the parallel and perpendicular components of net force. The parallel component, or p hat, is tangent and parallel to the direction of motion. The positive p hat points in the direction of motion, and the parallel component changes the speed and magnitude of momentum of the object. The perpendicular component, or n hat, is perpendicular to the direction of motion. Positive n hat points towards the center of the osculating circle, and the perpendicular component changes the direction of motion or the turning of an object. The final fundamental principle involved in this lab was the universal law of gravitation, or the gravitational force. This force follows Newton's third law, where the gravitational force on object 2 by object 1 is equal to the negative gravitational force on object 1 by object 2. The negative sign shows that the gravitational force is an attractive force. The gravitational force is derived from this formula, where g is the gravitational constant and r is the vector pointing from the source to the system. The overall findings from part 1 of this lab, we found that the mass of the black hole on average was around 1.5 times 10 to the negative 34, 1 times 10 to the 34 kilograms, where the final net forces are shown below. For this lab, the initial conditions are shown where the mass of the star is 2 times 10 to the 34th, where delta T is equivalent to around 1 day. In this computational model, we can see these initial conditions, as well as the calculations of the various components of net force within this while loop, such as the parallel components and the perpendicular components of the net force. We use this to calculate the mass of the black hole using this formula. Here is the program running. We calculated the mass of the black hole by rearranging the gravitational force formula, shown here below. Overall, the star follows an elliptical orbit around the black hole as the net gravitational force is not constant. As the star moves further away from the black hole, gravitational force decreases, and as it moves closer to the black hole, gravitational force increases. The changes in parallel and perpendicular components are shown in the lab, where the perpendicular component points towards the black hole, and the parallel component points in the direction of motion if it is non-zero. One source of error that could have taken place in this lab was rounding errors due to using g equal to 6.7 times 10 to the negative 11th. For part 2 of this lab, we found that the initial velocity of the spaceship is around negative 3.8 times 10 to the 7, 4.7 times 10 to the 6, 0 meters per second. Here is the second part of this lab. This is how we calculated the net force on the planet and the net force on the ship in order to calculate these final velocities and the position of the ship. For the velocity of the ship needs to move towards the black hole, so velocity x is less than 0. The ship needs to move away from the planet quickly enough, so the y velocity must be greater than the y velocity of the planet. To move towards the black hole, the x velocity has to be greater than the y velocity, and the ship cannot exceed the speed of light. The calculation of forces and velocities were shown in the lab. The spaceship initial velocity means that the ship is moving towards the left in the negative x direction and up in the positive y direction. The spaceship motion is changing as it enters the event horizon of the black hole due to the substantial force acting on the ship from the black hole. This means that the ship's speed increases as it gets closer to the black hole, and there's a change in the direction of motion. And since the speed of the spaceship is greater than the escape speed needed to escape the system, the ship can break free from the black hole at some point. The sources of error from this part of the lab are also rounding errors due to using g equals 6.7 times 10 to the negative 11th, 6.7 times 10 to the negative 11th, and because the initial velocity is experimental. What does it mean, net force versus rate of change of momentum? Net force is technically equivalent to the rate of change of momentum by Newton's second law. However, net force implies that analyzing forces that are acting on the object, while the rate of change of momentum implies analyzing the change in the object's motion due to those forces. What if you wanted to enter into orbit with the black hole in part 2? Then the initial speed should be smaller, so the magnitude of the velocity should be smaller. For this part, I experimented with trial and error and found an initial velocity of this, shown here, where the spaceship enters into some sort of orbit with the black hole without colliding in the planet, as shown to the right.